Okay, let's just jump right in. Welcome to this explainer where we are going to explore exactly how modern Java is evolving to meet the honestly staggering demands of the AI era. Specifically, we're zeroing in on how virtual threads fundamentally solve the massive scaling challenges of enterprise AI workloads. Look, if you've ever dealt with thousands of concurrent AI agents, you know that keeping a system both stable and fast is no small feat. It's a massive headache. So today, we're unpacking exactly how the Java virtual machine pulls it off.
We've got a lot of ground to cover as we descend what I like to call the JVM iceberg. We'll start at the surface with the AI concurrency crisis, move through the virtual thread revolution, and tackle managing the AI swarm. Then we'll dive deeper into memory and AI code generation, push deep Java to the metal, and finally hit the absolute bottom with real-time determinism. Let's get to it.
Section 1. The AI concurrency crisis and why traditional scaling fails. Let's start with the immediate problem staring pretty much every enterprise engineer right in the face. Modern AI workflows, like retrieval-augmented generation or RAG, and those really heavy LLM calls require massive amounts of I/O blocking. You are constantly waiting on external APIs, vector databases, network calls, and that sheer volume of waiting, it just brings legacy backend systems to their knees.
Now, we all know a lot of early AI development happens in Python, which is fantastic for rapid prototyping. But there's a catch. While that dynamism is great for early experimentation, it basically means many of your errors are only going to show up at runtime. And that is an unacceptable risk for mission-critical, high-volume enterprise pipelines. Java, on the other hand, provides the deterministic guardrails, the strong typing, the security models, the extreme observability that you absolutely need for a production environment.
But even in Java, we faced a major architectural dilemma when trying to scale up. Traditional platform threads? They'll crash your system by consuming way too much memory. Every single platform thread eats up about 1 megabyte of memory. So if you have 10,000 simultaneous AI requests, boom, you instantly need 10 gigabytes of RAM just to hold the threads, which exhausts OS limits incredibly fast. For years, the workaround was reactive frameworks. Sure, they're highly scalable, but they are notoriously complex. They create this unreadable callback hell and give you fragmented stack traces that make debugging an AI pipeline an absolute nightmare.
So how do we actually fix this? That brings us to Section 2, the virtual thread revolution, and making blocking cheap again. Let's look at how Project Loom completely shifts this paradigm.
Introduced fully in recent Java versions, virtual threads are lightweight threads created and scheduled directly by the JVM itself, not the operating system. And this is a real game changer because they require only a few kilobytes of stack storage instead of a full megabyte. This means you can create literally millions of concurrent tasks that multiplex over just a handful of underlying carrier threads. When your code hits a blocking I/O operation, like say waiting for that LLM response, the JVM simply parks that virtual thread and lets the carrier thread do other work. Suddenly, making blocking calls is cheap and completely natural again.
When you compare these approaches side by side, virtual threads match the sheer throughput of reactive systems, but, and this is huge, they give us back our sanity. Instead of writing complex flat maps and zips, we just write natural, synchronous, top-to-bottom code. Instead of fragmented debugging, we get complete, readable stack traces. It's an incredible example of how virtual threads improve concurrency simply by returning us to a mental model we actually understand, but with massive enterprise-grade scalability.
But writing the concurrent code? That's really only half the battle. Welcome to Section 3, Managing the AI Swarm. Because now that we can easily spawn a million threads, we have to actually govern these massive multi-agent AI swarms without bringing the whole system down.
If we just blindly fire off millions of virtual threads using unstructured concurrency, we introduce some severe dangers. Without proper governance, we're looking at heavy thread local memory leaks. And even worse, we get zombie tasks. Imagine a parent AI agent fails, but its subtasks, the ones out there querying a very expensive LLM, just keep running in the background. They're burning tokens and eating resources all because they didn't get the cancellation signal. Relying on wait and hope timeouts or swallowing interrupted exceptions will absolutely destroy an AI system's reliability at scale.
So we have to ask ourselves a pretty critical question. How can we safely control this massive increase in task volume across dynamic AI environments? How do we ensure that when a workflow gets canceled, every single tiny subtask is immediately and safely cleaned up?
The answer is structured concurrency. Think of it as the ultimate governance layer for our virtual threads. It treats a group of related tasks as a single nested unit of work. So if a parent agent fails or times out, the framework automatically cancels all of its associated child subtasks. It instantly prevents those resource leaks and zombie tasks. It makes your massive AI swarm inherently predictable and, most importantly, observable.
Going a bit deeper under the surface of our iceberg, we reach Section 4, Memory and AI Code Gen. We really need to look at how developers are actually writing these systems today and how the JVM manages the massive memory footprint underneath it all.
Interestingly enough, one of the best tools for building these complex Java AI backends is AI itself. AI-assisted generation accelerates all that routine boilerplate scaffolding, things like REST controllers and data transfer objects. This massive reduction in manual effort is great because it allows developers to focus heavily on the intense human oversight required to design safe architectures and prevent thread unsafe concurrency issues. AI helps write the code, sure, but human engineers absolutely must design the structured concurrency.
And while all those millions of virtual threads are humming along, they are allocating massive amounts of memory objects. To handle this footprint seamlessly, modern garbage collectors like G1, Shenandoah, and ZGC deploy sophisticated read and write barriers. Basically, these are tiny pieces of extra memory management code that execute quietly behind the scenes. They allow the JVM to safely track references and compact memory concurrently without ever pausing your AI threads. This is exactly what keeps your latency low, even when the system is under incredible load.
Now we plunge into the true depths of the JVM. Section 5, Deep Java to the Metal. We have our threads, we have our memory governed, but how do we map all this concurrent data directly to AI hardware, like GPUs, to get maximum performance? Historically, connecting Java to native C libraries or GPUs required the Java Native Interface, or JNI, which was frankly slow and cumbersome. But today, we no longer have to rely on slow JNI glue code. We now have 3 direct paths to the metal. Project Panama gives us the foreign function and memory API for incredibly fast off-heat memory sharing with CUDA. The Vector API lets us explicitly trigger SIMD instructions to accelerate matrix math right on the CPU. And Tornado VM acts almost like magic, compiling pure Java code ahead of time directly into GPU instructions. And this builds into what some developers are playfully calling the forgotten gods of Java's future, the holy trinity of the JVM. Project Valhalla will soon introduce true float 16 value classes, giving us zero overhead type-safe math, which is absolutely crucial for AI. Project Babylon brings code reflection, allowing tools to deeply analyze Java code. And the Heterogeneous Accelerator Toolkit, or HAT, translates that reflection directly into optimized GPU kernels. Pretty soon, developers will write pure Java that translates directly into high-speed GPU execution, completely bypassing the need for Python or external model files entirely.
Finally, let's look at the absolute bottom of our iceberg with Section 6, Real-Time and Beyond. Because believe it or not, there are specific high-stakes domains where even standard JVM hardware acceleration still isn't quite enough. We are talking about sub-millisecond hardware-in-the-loop applications. Think robotic oil rigs, power plants, defense systems. In these environments, standard JVMs just fall short because they can suffer from unpredictable garbage collection pauses or just-in-time compilation delays. I mean, if an AI agent misses a millisecond deadline on a robotic oil rig, the whole system fails. But tools like PTC per step in to guarantee real-time execution. They bypass JIT compilers entirely, using ahead-of-time compilation. They enforce a deterministic garbage collector that never pauses priority tasks. And they utilize strict priority thread scheduling directly with the operating system.
Which really brings us full circle. From fundamentally solving the AI concurrency crisis at the surface level with virtual threads to compiling straight to the GPU in the depths, Java has evolved from a simple backend language into a deeply scalable, synchronous-first engine. With virtual threads making blocking cheap and native APIs seamlessly unlocking the metal, it leaves us with one final, pretty exciting thought. What limits are truly left for Java in this new era of intelligent systems? Thanks for joining me on this explainer, and I'll catch you on the next deep dive.